Okay, section 4.5, Undetermined Coefficients, which is the same header as it was in 4.4. It was the undetermined coefficients. There it was the superposition approach. So here, this approach says to be some type of operator that wants to cancel out a term, a function, or a derivative. And it doesn't have to be a derivative. It could even be an integral. But what exists to annihilate, to somehow get the kernel or to get zero from applying a certain, we call it here an operator onto a function to get zero. And so our goal is to be able to solve this problem, y double prime plus 3y prime plus 2y equal to 4x squared. We solve this using the superposition approach by we first solve for the homogeneous part, and then we solve for the non-homogeneous part by looking at here g of x, which equals to 4x squared. And so it's 4x squared, so it's quadratic, so we'll let y sub p equal to ax squared plus bx plus c. So we did that back in section 4.4, but here in this section, what we want to do is to ask the question, what derivative, if we can claim the derivative as being an annihilator or operator, I should say. An operator is a function that when applied to another function that somehow it changes the form of that function. Think, a derivative, which is some function applied to a function, it changes that function, right? So if you give me 5x squared, I can return by operating with a derivative, I can give you 10x, right? So this operator, it operates just like a surgeon would operate on a person, and then the result, something changes, hopefully for the good, right? And so here we want to be able to operate. We claim here the definition. A differential operator is a derivative sometimes denoted with a capital D. There are several operators in mathematics. Can you name another operator besides a derivative? An integral, exactly. Right? The two main operators that we've dealt with in calculus. Either we apply the derivative on a function or we apply the integral of a function, right? Take the integral of a function, I get a different function, right? So here the integral also operates. The derivative also operates. In algebra, you dealt with the composition function. You can compose a function with another function. That also was another idea of an operator. So here, a differential equation such as y double prime plus 4y prime plus 4y equal to 0 can be written in terms of the operation notation where you replace the derivative with a d. So here, that becomes d squared plus 4d plus y, all operated on y. So d squared plus 4d plus 4, all operated on this y. If you can factor, then that's good. You can factor that into d plus 2 times d plus 2 operated on y. And we read that is equal to 0. And then you can simplify that. That's just d plus 2 squared operated on y equal to 0. Now the operator may not itself be an annihilator, but we can take the operator and in so many iterations we can annihilate a function. Say for example, if you have 5x squared, how many derivatives can I apply on 5x squared to get 0? 3 derivatives, right? Take the first derivative, you get 10x. Take the second derivative, you get 10. Take the third derivative, you get 0. That's going to be our goal, to use the annihilator approach to somehow form the solution model for the non-homogeneous differential equation. That's our goal. So let's see if we can put that together in pieces. So here, represent the following differential equation using differential operators. So this is simply parentheses d squared plus 3d plus 2 operated on y is equal to 4x squared. Now, if you can factor, factor. If not, leave it alone. So we can factor that. D plus 2 times d plus 1 operated on y is equal to 4x squared. Now the so-called annihilator is here. What linear differential operator exists such that when it's applied on a function f, I get 0. So here, this capital L is called annihilator. Right? I want to be able to cancel out the function. So here, if the differential operator is a derivative, then how many derivatives can I apply on the function to get 0? That's all they're saying. Now, here are some standard d to the n annihilator operators. Say, for example, if you have a polynomial, the polynomial is of, say, for example, the second degree, then obviously I need d to the third, power to annihilate that. So here they go up to n minus 1, and so you take dn to cancel out whatever term that you may have. For an example, so here, if f of x is equal to, say, x to the third, so here, d on f of x is 3x squared. D squared applied to f of x is 6x. D third applied to f of x is 6. So the fourth derivative applied to f of x is 0. So without even, going through all those steps, here, just that neat formula that if I have the polynomial of its highest degree, then it's that n plus 1 term that will annihilate that in terms of the derivative, right? So basically, d to the 4 is what we need to get rid of, to annihilate here the function f of x equals to x to the third. What if you have terms like, just say y is equal to e to the 4x? So if that's the case, here where alpha is equal to 4, so the differential operator is d minus alpha, or d minus 4, here operated on y, that gives us 0, just based on this schematic scheme, based on those terms. So if that be the case, now this differential operator on y is 4 times e to the 4x. So this d minus 4 times y is understood to be the differential operator on y minus 4 times y. Well, let's see. Well, this differential operator on y is 4 times e to the 4x minus 4 times y. Y here is e to the 4x. Well, we get 0. Okay. Now, if it's x times e to the alpha x, or if it's x squared times e to the alpha x, you look at the x's as you did above here. Well, if it's x to the n, or n minus 1, then you use d to the n. So here, if it's repeating terms for the exponential guys, here e to the alpha x, there's no repeat there. But here this is said to be, this guy is repeating there one time. So I'm going to use the next number up. So if this is x times e to the alpha x, then I'm going to use d minus alpha here to the second power to annihilate that term. So then what about if you have combinations of exponential some e base times a cosine, their repeats, whether it's sine or cosine? I'm going to use this very sophisticated formula. Now here, if you have a problem like that, just use the formula, just find that formula, and you're done. Again, I do not require anybody to memorize anything, so I'm not going to give you a problem like that. So if I did, I'd give you the formula, okay? But it's very self-explanatory. Just plug that in. So anyway, I do not grade on memorization. I just grade on knowledge. But what I will have for you is if you have the case where it's just a cosine or a sine, and that's very straightforward. So if it's just cosine or sine, like if it's cosine beta x, or if it's sine beta x, where here beta is that number that's said to be associated with x. So whatever that number is going to be d squared plus beta squared applied to that particular function. Let me give you an example there of that one. Let's say if y is equal to cosine, let's say 6x. Right? So what this is saying is that to get rid of the cosine 6x, this is d squared plus 36 applied to y. That's supposed to give us 0. Well, let's see if it does. So here, d, the first d, that first derivative is going to be negative 6 times sine 6x. Then that d squared is negative 36 times cosine 6x. So if I take d squared here, apply it to that y, plus 36 times y, well, that d squared on y is negative 36 cosine 6x plus 36 times y. Y is cosine 6x. I get 0. Okay? So if I will give you like a single cosine or a single sine, what annihilates that? It's the d squared plus the beta squared. Right? Now let's look at some problems. This statement here that I have above is very important. Suppose L sub 1 annihilates y sub 1, and then suppose that L sub 2, what's the L? It's the differential operator that annihilates. So suppose L sub 2 gets rid of, cancels out to 0, y sub 2. Then the product, L sub 1 times L sub 2, annihilates the sum here, C sub 1 times y sub 1, plus C sub 2 times y sub 2. This is coming from the superposition principle of how you would write solutions here for a homogeneous differential equation. Before I would prove that, I want to show you some problems. My time is running up. I just gave that sermon before I went into 4.5, and it was kind of lengthy. I think I took about 45 minutes to preach that sermon, which is almost typical to what happens on Sunday morning, too, at about 45. And folk, they get on me about, we're holding service a little bit too long there. Well, it may be longer like that in hell, So just be thankful that, we take these 45 minutes right here to expound on the word. So anyway, typically I do prove it to show that, because it looks strange that why would the product annihilate the sum? You would think that the sum of L1 plus L2 would get rid of C sub 1 times y sub 1 plus C sub 2 times y sub 2. You don't see it unless you see that proof. And the proof of it is very simple. Basically, you take L sub 1 times L sub 2, parentheses, on the C sub 1 times Y sub 1 plus C sub 2 times L times Y sub 2, and it does get rid of that. The sum of L sub 1 plus L sub 2 would not cancel the sum of C sub 1 times Y sub 1 plus C sub 2 times Y sub 2. But anyway, here, write the differential equation in the form L sub y is equal to g of x, where L is the differential operator with constant coefficients. If possible, factor L. So here, all they're saying is that this is 9 times d squared minus 4 parentheses times y is equal to sine x. That's all they're saying there. Here, this is just d squared minus 4d minus 12 parentheses applied on y is equal to x minus 6. Now, we can factor that one. This is d minus 6 times d plus 2 on y is equal to x minus 6. And you get the picture, right? So if it's this one, this is d times d plus 1 times d plus 3 on y is equal to, you always just write the right side as it is. We'll deal with that when we actually go to solve using this this concept. Okay. Verify that the given differential operator annihilates the indicated functions. So if you simplify this, this is just d squared plus 3d minus 10, all applied to y, is supposed to give us 0. So what we need is to find d squared on y. So here, this d of y is 2 times e to the 2x minus 15 times e to the negative 5x. And then the d squared on y is 4 times e to the 2x here plus 75 times e to the negative 5x. So we're going to put this into this form here. So this is d squared on y plus 3d on y minus 10 times y. Let's see what that is. So this d squared is that 4e to the 2x plus 75e to the negative 5x plus 3 times d, and d was parentheses 2 times e to the 2x minus 15 times e to the negative 5x. And then this is minus 10 times y, and y is this guy right here. So minus 10 times e to the 2x minus 10 times 3 is minus 30 times e to the negative 5x. Well, here, let's simplify that. So this is 4e to the 2x plus 75e to the negative 5x plus 6 times e to the 2x minus 45 times e to the negative 5x minus 10 times e to the 2x minus 30 times e to the negative 5x. Right? So let's look at the e to the 2x's. So this is 4, that's 6, that's 10 minus 10. Well, they go out. And then this is 75 here, and this is minus 45 minus 30. Well, that's minus 75. plus 75, so they go out. So that's equal to 0. So we just verified that indeed this annihilator here does cancel out that y. Right. Well, I got time for just one more problem. Here we want to solve. Oh, well, these are these guys. Let me just run through this real quick, and then we get to where we have to actually solve a non-homogeneous differential equation. What happened to my printout there? Find the differential operator that annihilates the given function. Well, what annihilates 1? D, right? What annihilates d x to the 6 times x, excuse me. That's d squared. What annihilates here 2x to the 3rd? That's going to be d to the 4th. But since they're all in the same form, right? You just need one of them. That's the d to the 4th. Right? They're in that same family, if you will. So that d to the 4th is going to cancel out everything, right? What about 17? Now 17, this 1 is not in the family of e to the 2x. So this is a sum. Oh, I know what that was. Ah, mercy. Ah, yeah. It's that guy. Dang on it. That's what that was. I put that statement there because this 1 is annihilated by d, comma, this e to the 2x is annihilated by d minus 2. Right? They're different. So here d, which is actually L sub 1, that's what that is going to annihilate this y sub 1, which is 1. And then L sub 2, which is d minus 2, is going to annihilate this 7 times e to the 2x. So to annihilate the whole thing, it becomes the product of the annihilator. So here, the answer is d times d minus 2. The product of the annihilators annihilates the sum. This cosine, again, beta is 2, so this is just d squared plus beta squared, 4. That's all we need there. Here, d annihilates the 1, and then d squared plus 1 squared annihilates the sine x. All right, so 13x plus 9x squared is annihilated by d to the 3rd, comma, the sine 4x is annihilated by d squared plus 16. It's the product then that you need, d to the 3rd times parentheses d squared plus 16. Now, let's solve a problem. Solve the given differential equation by undetermined coefficients. Let's see which one will be a better one. I think 37 is better, so let me do that one. Here, the first thing you do is solve y double prime plus y prime equal to 0. Well, we've done that before. So this implies that the auxiliary equation is m squared plus m, that's equal to m times m plus 1 equal to 0. So m equals to 0, m equals to negative 1. So this implies that y sub c is equal to c sub 1 plus c sub 2 times e to the negative x. Now, solve y double prime plus y prime is equal to 13 by this method. To solve this, you're going to ask the question, what operator annihilates y double prime plus y prime, or let me say this, what operator represents y double prime plus y prime, and then what operator annihilates 3? So that's the question. So what operator represents y double prime plus y prime, and what operator annihilates three. All right. So here, d squared plus d represents y double prime plus y prime, and d annihilates this 3. So if that's the case, the way we work this is we say since the d annihilates the 3, it's that d there times d squared plus d here gives us 0. Now look at this. This is d times d. I can write it like this. I'm factoring out a d from here. So this is d times d plus 1 is equal to 0. Right? If I take, this is d squared times d plus 1 is equal to 0. If I take this representation and apply this to the constants, this says that y is equal to, this first d is a constant that it annihilated, and then plus some, that second d is a repeat, so it's c sub 2 times x, plus, in other words, this is d equal to 0, d equal to 0, d equal to negative 1. And so this is plus, so this first d is c sub 1 times e to the 0 times x, which is a c sub 1, plus here, this is the same term, but it's times a repeat, so it's times x, plus I pick up this d equal to negative 1. This is c sub 3 times e to the negative x. But didn't we get part of that up here? See this c sub 1 plus c sub 2 times e to the negative x? Well, that's this guy and this guy, right? Now look at 3. For the old method, you would say let y sub p equal to 3, but that 3 is a constant, which is a repeat of c sub 1. So then you would say, for the glitch problem, you would say let y sub p equal to a times x. Well, it's fixed here. You see that? C sub 2 times x is fixed. So now we have to actually solve to see what's actually in front of that x. That is, resort back to using the superposition approach. Again, this method in 4.5, it only fixes the glitch. We're still using the same superposition approach from 4.4. So here, using the superposition method from section 4.4, let y sub p here equal to, it's this c sub 2 times x, or you can write that as just a times x. Y prime is equal to, it's not linear to be ax plus b, because remember this g of x was just 3. It was just a constant. So the next term up for the repeat would be a times x. So y prime here is a, y double prime is 0. So I take the original problem, which is y double prime plus y prime equal to 3. And this gives us y double prime is 0 plus y prime, that's a, that's equal to 3. That implies that a is equal to 3, but y sub p is a times x. That is 3x. So thus, y is equal to y sub c plus y sub p. This is c sub 1 plus c sub 2. Can move that to e to the negative x. Then plus the particular solution plus the 3x. Well, that 3 was really a constant up here, but we solved for it, right? And we got a 3 there times that x. Now it's c sub 1, c sub 2, and c sub 3. We reordered that because up here was c sub 3 times e to the negative x. Here I got c sub 2 times e to the negative x. It doesn't matter about the reordering as long as you have it in this form here, that there has to be a 3x in that solution plus some constant, then plus some constant times some e to the negative x, right? That's it. 5 minutes over, but I did a little preaching, so the preacher goes over every now and then. Have a good weekend. Do the homework in this section. You should be fine with that. I'll try to work one problem or two from here on Monday, and then we'll go into a very important section, variation of parameters. Thank you.